So I should start with this book. Yeah, so I want to give some introduction to my yeah. So the motivation is as follows. So let's say P is a prime number. So if you start with a modular form, so well, I should say cuspidal eigenform. Then you can attach a two-dimensional Galois representation. Yeah. So GQ will denote the absolute Galois group of value in P. All right, so and so this we'll start with F, and then this I will call rho F, and so let's say the weight is K. So this map, when K is at least 2, well, when K is 2 is the classical theory of Shimura, and general by the link. And when case 1 is the link set. Yeah, of course, it's just it's not a random map between these two sets. I mean, you want the Fourier coefficient here matched with so normal. If you normalize it, so you want the high eigenvalues match with the trace of Frobenius here. And actually, it's not just a random two-dimensional Galois representation. So actually, it enjoys some nice properties. So actually, it's continuous, irreducible. I mean, these properties were proved that, well, continuous was proved when they constructed, but these properties were proved later on. And moreover, if you let me call it rho, restrict at the decomposition group at L, then this is unramified, which means the image of the inertia is just trivial. This is not for almost all L. This tells you for generic places it's unramified, and at the infinite place, so this is just the order 2 group. This is non-trivial. So maybe I want to say the determinants of this is non-trivial. This is usually called odd because it's order 2, so either it's trivial character or the non-trivial character. Here, actually, it turns out it's a non-trivial character. In the end, the loss is that what's happening at P is that this is the wrong of Hodge-State's weights, 0 and K minus 1. I will remind you what Hodge-State weights means later. So this was proved later on after people have developed enough object choose to study the Galois representations. And so this is just a map of from this slide from automorphic forms to Galois representation, and the famous conjecture of Fontaine-Mazur. Essentially, well, let's say this is only up to isomorphism class. Is that actually this map is surjective. Okay, actually, it's easy to show it's injective just based on the high eigenvalues correspond to trace of Frobenius, and trace of Frobenius by Kapitov density just already determine a Galois representation. So this conjecture says, well, it's actually a bijection. Okay. So this conjecture, so of course, it's very now we actually know most of the cases, but already a very natural question you can ask the this is instead of this very general form, you can ask the following. So already, if you just I mean, I'm not starting from an arbitrary two-dimensional representation, but just suppose I have a sequence of modular forms, not necessarily of the same weight, and let's say say eigenforms, and say their Galois representations actually converge because they take value in GL2 QP bar. There's natural p-adic topology there, and say right here, say the limits actually it exists. And let's say rho is the limit of this rho fi, and actually satisfy these these conditions. So same conjecture. And of course, you expected that but if this conjecture predicts that rho comes from some modular form, but of course, so rho equals to some rho f.
Can I ask a question about this? So each of the rows of Fi is a superconductor conjugation, right?
Yeah.
So what's the limit mean in that setting?
Yeah, that's a good question. So I'm trying to be very vague here, but I want to just fix a homomorphism to GL2QP bar and assume they actually converge to something. Yeah, that's what that means.
But you could also take the limit of the cactus monomials.
Yes.
And then from that you could reconstruct it to do it. If that has a nice limit, then you can reconstruct it.
Yeah.
And is the round condition magically followed?
No, that's the thanks. That's the key point. So in general, the limits will satisfy when the fix the level away from P, it will satisfy these conditions, but not this one. But let me assume it's still the realm of Hodge-shaped weight 0 k minus 1 of some integer k, and you predict like the conjecture predicts it comes from some modular form, but now the question is why? So of course, for people who are familiar with the congruences of modular form, so you can easily cook up a modular form, p-adic modular form. You just say actually the sort of the limit of fi exists in some p-adic sense, but usually you just get the p-adic modular form, not necessarily a classical modular form. So the question is, so how to find such f? So in this, I would say in this very special case of this conjecture, so actually it was a theorem of Emerton, and the answer is yes. So actually he proved that if this rho, let's say, is the realm of Hodge-shaped weights 0 in k minus 1, and this k minus 1 is at least 1, then the math showed that actually you can find a classical eigenform of weight k whose associated Galois representation is equal to rho. So to attack so answer this kind of question, so Emerton used some kind of a representation theoretic tools, and the key object here is what he called the p-adically completed cohomology. Okay, so I'm going to actually, and then he even reduce the general Fontaine-Mazur conjecture to this special case and solve most cases of
I think you remember that the exact thing also comes from some limit considerations.
Yes.
But well, actually done by hand.
Yes.
Is this do these two things are anyway related?
Yes, they're related in the sense that they are the congruences, but more than that I couldn't quite say much. There is. In the k equal to 1 case, you do not construct the row directly, but you really construct through writing rho as the limit of rho Fi. Any other questions?
Maybe what you could say is that sometimes you can choose the f's carefully to go to some other, like you could choose the f(i)s to go to some f that you like away from one guy. You could also choose them to go to some other kind of Q expansion that's at a Geiger form that you know is not coming from any classical way. So there are lots of different there are lots of different ways to there are lots of different rows you can make sometimes. So lots of different and then
let me come back to a completed cohomology. So my understanding of this is that if you just stare at this picture, you're just working with modular forms. There's not much geometry. There's no geometry. You can't really use tools from geometry. So I'm going to introduce this completed cohomology to put you in some geometric context, and you have more tools from geometry to study all these things. So let me quickly give a definition of this completed cohomology. So my notation is as follows. So if you have a neat open compact subgroup of GL to finite del, then we can define the usual modular curve. So it's an algebraic curve defined over Q, but these complex points are simply given by the usual double coset. So you have the union of upper and the lower half plane times GL to finite del. And the GL2Q acts diagonally on these two. This section here is just the usual modulus transformation. So for people who have never seen this can be written as just some this is my notation for upper half plane. Quotient by some congruent subgroup, and is in general some disjoint union of quotients of this form. Okay. And the idea here is that you fix the level away from P and vary the level just at P. Okay, so let me just assume K even has just this special form. So K upper P is the open compact subgroup of GL2 finite del away from P, and K lower P is just the open subgroup of GL2, open compact subgroup of GL2QP. And then you can just here's the definition. H delta I actually depends on this K upper P, but not write it here. So you take the cohomology of this modular curve. Either you can just use the Betti cohomology, or just using the comparison theorem, I can just use the État cohomology. Motion coefficient. And so I first take the direct limit over all the level at P. Okay. And then I take the inverse limit over N. And so this is the completed cohomology obtained level K upper P. So usually what people do is that you just take the ZP ZP coefficient cohomology, and then you take the limit, direct limit over OKP. Actually, it's closely, both are closely related. So actually, if you you first take the direct limit over O level. It's a ZP coefficient. And take the direct limit over OKP. And then if you p-adically complete this limit, because if start with something p-adic complete, but after taking the co-limit, they won't be anymore. But now you get it completed again, actually, it just agrees with this definition. So in general, this is the definition, but in this special case of modular curve, you can also take this as the definition. So clearly from this description that it's really just some p-adic completion of cohomology, so cohomology of a usual modular curve.
So just to clarify that because these objects are torsion free in this case, it's not.
Yes, it is exactly because curve. Yeah. Thanks for the comment. Yeah. And this what I want to. There are a lot of symmetries here, but what I want to use it here, because you take the limit over O level at P, so you have a GL2QP action, and also because it's defined over Q, so you also have a absolute Galois group acting on everything. Okay. And
Maybe you can put the other one up.
oh.
If your weight is not too still, you should put some coefficients as usual. That's no problem.
Let me make a comment on it. That's a very good question. So here, if you look at this definition, I'm only just using constant coefficient. So you think it's just related to weight 2 module formed by the Escher-Schmor relation. But the point is that after I take a sort of using this kind of congruence, actually I see all the weights by the following fact. So this for K is at least 2. So I have the algebraic representation same K minus 2 of the standard representation. This is the representation of GL2. And so using this, I can just I just get a p-adic local system. Okay, it's my p-adic local system. On my modular curve. And usually the cohomology of this LK by the Escher-Schmor theory is related to modular form of weight K. And actually, this cohomology, you can also see it in the completed cohomology in the following way. So, correct. Such a, if you take the H1, of this local system, and it's just a isomorphic to home as a KP representation from this representation, the due of this representation. Maybe let me just be more precise. QP standard representation, and then you take this huge, which is due to at least operating version P. This is one case, at least 3. One case 2, you still have an injective map. You just need to modify by some Eisenstein series. But the difference is very small, so you can ignore that. But the point is that even though you're just, this is defined just using weight 2 forms, but you can also see higher weights. So the point is that the formula here is that you need you need to home of some algebraic representation as a KP representation to a completed cohomology. Then you see classical like weight form, classical forms of weight K. Yeah. So this is related to rho F, and F is the eigenform of weight K by the usual Schwarzschild theory. So I guess so now I can just say what actually Matt actually proved. So you should think that this assumption rho is the limit of rho I phi really tells me actually it's a non-trivial result, but you can really show that this rho shows up in H theta 1. So just assume home of rho as a GQ representation appears as a sub-representation of the completed cohomology. Yeah, I forgot to say, so this H theta I can define for any I, but for most I, it's not very interesting. Only for I equals 1. I mean, I equal to 1 is the most interesting degree. So you can just home this rho, the scalar representation in H theta 1. Let me give a name and call it pi rho. And just assume, if we assume this is non-zero, I mean, this is another way to say my assumption there. And assume that rho is the ROM of Hodge-Higgs weights 0k minus 1. And let me assume this. And we are in the regular case, meaning that these two numbers are different. So what Emerton really proved is that this pi rho is really represent, because the action of GQ and GL2QP, they commute, so this still carries an action of GL2QP. Okay. So what Emerton proved is that in some sense, this if you home, this what's my notation there? It's the same k minus 2 p squared theta 1. Sorry, pi rho is not 0, at least for some KP. For some open subgroup KP, and you see that's how he deduced that actually such rho comes from modular form, because once you know, like pi rho has such a, usually we call the image we call locally algebraic vectors. Once pi rho has locally non-zero locally algebraic vectors, but the locally algebraic vectors of the whole completed cohomology are just related to modular form of weight K. So you deduce that this rho actually really comes from some modular form of weight K. Okay, so then the highly non-trivial step here is to really show that the existence of this. So in some sense, the most non-trivial step is to show this pi rho a priori is just it is an infinite dimensional representation, but it really has a finite dimensional sub-representation here. And to do this, actually, what crucially goes into Matt's proof is that the p-adic local Langlands correspondence for GL2QP. Okay, I'm not going to say anything more than that. I'll just say it's a very nice correspondence. So you can use that to study such kind of problem in this case, but I also emphasize it's only for GL2QP. So we essentially don't know anything if we either replace 2 by any larger number or replace QP by any finite extension. So it'd be nice to sort of revisit this result of Emerton and try to find a different way to think about this. So what I plan to do in my talk But now I realize probably I'm too ambitious. So hopefully by the end of the next talk, I can explain at least one thing is that I'm not going to really tell you to prove that well, this pi rho has this finite dimensional sub-representation. So, but I want to prove the following thing. At least sketch a proof of the following thing. So pi rho is a GL2QP representation. Actually, it's a Banach space representation. And I want to consider a dense subspace. LA is you take the GL2QP locally analytic vectors. Just meaning that yeah, so just as a representation theory, usual representation theory of Lie groups, you want to study the Lie algebra action. But the algebra action really comes from taking derivatives. So the first thing you need to do is to make sure the action is smooth enough so that you can take derivative. And it turns out that you can't take derivative for all the vector, but at least for the local analytic vectors, which really just means that locally around the identity component elements, that the action is given by a convergent power series, so that then you can take derivatives. So a priori, there is not clearly there exists such a vector, but actually a very nice result of Schneider and Tetrabaum tells you that in this case, this is really a dense subset. So you don't lose much information. This is dense. And once you look at the local analytic vectors, now we can talk about the Lie algebra action. And so the goal I want to explain is that so pi LA, now it has the action of the Lie algebra GL2. And then you can just look at the infinitesimal character. Really just means that you look at the universal enveloping algebra and you take its center. Which is has a nice description given by Harishchandra. So the goal is that pi rho LA has the same infinitesimal character as this one, this finite dimensional representation. So of course, this is
just a moment. And where was K there?
K.
You have symmetric power K minus 2.
Yes, so K is determined by the hot-shaped weights.
By the hot weight. Okay.
Yeah. So
sorry.
No, that's a very good question. So actually, this result holds not just for de Rham representation, but just for arbitrary representation. You can make sense of hot-shaped weights, and if we show up here, then actually this is true, and then you can imagine what's replaced there. Yeah, but the point is that the rho determines hot-shaped weights and actually determines the infinitesimal character of this GL2QP representation. A priori, it's not even clear it has an infinitesimal character, so that's part of the claim here is first it has an infinitesimal character, and this infinitesimal character is precisely given by this hot-shape.
But the fact is that it decomposes just direct sum of those, or what completes a direct sum. Or there could be some complicated.
Yeah, it's much more complicated. Yeah, it's not like just completed direct sum. Yeah, it's more complicated. Yeah.
So just I mean true infinite dimensional things could occur there.
Yeah.
I mean true infinite dimensional representations of algebra can occur there.
Yeah. Yes.
Okay. So we kind of varies in the better module and kind of things and stuff.
But also finite.
So it also is finite. Yeah, if you assume the round, also is finite dimensional.
Yeah. But yeah, this is just the some part of it, but also there are in general you will see some version inside and some completion of that. Yeah. Yeah, so that's my goal. Other questions?
So can you say a little bit more about what the whole I of rho LA looks like? Is more explicitly.
So that's the definition. So
Yeah.
I know rho is the sub-representation here. So I just take the rho isotopy part. So I take home rho into it.
Sorry, but I meant like so it's a GL2 of QP representation.
Exactly.
So you said it has some like very large infinite dimensional pieces, and it's
infinite dimensional.
yes.
Yes.
But okay, but it is very far from being irreducible.
Well, in some case, I think we know it. In this case, it's not irreducible. Yeah. I think it always has finite length as the GL2QP topologically a finite length, but that's also not easy to prove. Yeah.
But the kind of thing you should imagine is some kind of parabolic induction, like in smooth group 3, but just make it a modular curve. And instead of defining it like smooth functions, think about what the big function satisfying the parabolic induction. Modular curve. And even if you do a smooth character, you can still talk the local function in the parabolic induction. And then that will have a smooth parabolic induction inside of it. That's the way that this guy decides to have constituents.
It's like very nice question. So if you just have a modular form, like explicit modular form,
Yeah.
How explicit is this?
I mean, it depends whether it's supercustal. If it's principal series of P, it's so it's just given a supercustal of P, it's a little bit less.
Yeah. So we do have some description in this case. But it depends on what you mean by explicit. Yeah, but the modular forms are here just contribute to this part.
And if your level prime, if the KP was GL2C, so if you were level prime in P, then it will be an extension of two of these local principal series.
But when we define principal series, you need to consider what something's black. But the thing is J2 of KP also J2 of KP representation. But it's
This is in some sense why you have two. So in the classical theory, there's an intertwiner.
Yeah.
Which means that so it doesn't matter which 5 you choose.
Yes.
And in the p-adic theory, there are no intertwiners, so it matters. So it matters which 5 you choose, and this is why you get kind of get two principal series.
See,
But he's not going to do this.
Yeah, sorry, I'm not going to do it today. I'm not sure I will have time next time. But yeah, so I would say the finer structure of this representation is very interesting, and that's the whole point of this p-adic local Langlands correspondence to really understand the structure of the. Yeah, so yeah, what I'm going to explain today is just some very, very weak results in some sense, like just infinitesimal character or these kind of things. But yeah, of course, it would be nice if we can understand this representation pretty well, but that's hard in general. Okay, so before starting doing that, I mean, this is so far everything's p-adic, but still I want to tell you something just over the real number or complex numbers. Actually, that's all my motivation actually comes from. And so I just want to explain to you why you should expect that the infinitesimal character has something to do with some weights coming from Hodge's theory. Okay, so actually you already have implicitly seen this in the complexes story. So this complexes picture or real picture is what people use. At least some people, at least when I read the literature, is called the Kugas formula. I would just explain in the simplest form, and it's so simple that I don't think anyone will call it Kugas formula, but Kugas, the generalization is, I just consider the usual upper half plane, and it has the action of SL2R by the usual Mobius transformation. Okay, so on the upper half plane, let me remind you, it's a hyperbolic space. It has its remaining manifold with constant curvature -1. And you have to, so on this upper half plane, so you can define the hyperbolic Laplacian. Okay. On the other hand, because I have an action of SL2R, so it also acts on the smooth function, C infinity function on the upper half plane. And then I have the Lie-algebra action because I can differentiate. Again, I can consider the action of the center. And there's a particular element in the center which generates a center, which is the Casimir operator. Okay. And this is the Casimir operator, which lives in the SL2. Okay, and it turns out that these two are not, they are just related, they just differ by a sign. When it acts on the smooth function on it. And actually, this is a simple equality. Actually, you should regard that that's in the real picture actually gives you this relation. Why? So now let me try to compute the cohomology of arithmetic quotient of upper half plane. So let's say gamma is some arithmetic subgroup. And for simplicity, let me just assume it's co-compact. And then maybe also put these just to have a nice quotient. So when you compute the quotient of the cohomology of H mod gamma, at least let me do this first, the C coefficient. And you can use the Durand. So this is a very nice complete curve, and you can just compute the cohomology using Durand theory, and you can rewrite the Durand complex, and that's usually identified. And you can actually identify this the GK cohomology of the space of automorphic forms on G mod gamma. It's the C coefficient. Let me explain my notation here. So G is just the Lie-algebra of SL2. And K is the maximum open compact subgroup. In this case, it's just SO2. And this notation just means the space of automorphic forms. And G is just my SL2. So this is my G. So this is usually called the similar formula. But actually, in this very simple case, you can just, it's not too hard to prove. But now the point is that I want to apply this result. So by Hodge theory, I know that for if I use for each representative, like if I look at the Durand cohomology, it has a unique representative given by harmonic form. And so for that means that so I should regard the cohomology class here are harmonic forms, which means Laplacian is 0. But Laplacian 0 here just tells me that actually the Casimir also acts 0. So which means that actually here not all the automorphic representation will contribute to the cohomology, but actually you very roughly speaking, you can only see the one. Let me just use this note. I'll just write here. Those with the trivial, because it generates at the center. Actually, the center acts trivially. So, so this is just because of Kugas formula. So you see that so the cohomology here, you will only see that those representation with trivial infinitesimal character, and that's more or less some very weak relationship between like what you see for the Hodge theory and what you see for the infinitesimal character. And actually, what's more in this case is that actually this is a algebraic curve. So actually, it has a you can do the Kähler. You have even the complex Hodge decomposition. And so in principle, you should also be able to see this PQ grading on the right-hand side. So actually, in some sense, if you unravel all the construction, that means you are basically asking where does the complex structure of upper half plane come from? But the complex structure of this really just comes from the action of the Lie-algebra, the adjoint action of this of K on the Lie-algebra. Even you can just take the Lie-algebra of K. That gives you this PQ grading. So in the p-adic case, what we are going to replace we will replace instead of talking about Hodge decomposition, we will replace by the so-called Hodge state decomposition. But still, we want it to be explained by some kind of adjoint action or some action of the Lie-algebra. So that's basically what I want to present. So first is sort of this thing. There won't be exactly the same formula, but at least if you see here, this is really a local statement here. I'm not going to write down, but it has nothing to do with H mod gamma. I want to emphasize here, this is really a statement for H, for the universal cover of your arithmetic variety. So that's the first thing. So this is really a local statement. And also the second thing is I want to have a similar sort of this kind of reading coming from some Lie-algebra action. That's the plan. Okay, and now I'm going to start doing p-adic stuff. But I hope this real picture is helpful. At least this the hope, like it's the whole motivation for me to do this p-adic.
Somewhat similar picture if you have a non-integral Hodge state weights.
Yes.
So what you will explain actually will cover that.
Yes, exactly. Yeah. I hope you do. Yeah. It's I just look at time. I realize probably I don't have time, but today, but at least next time. But because I think first I want to just erase this Hodge state weights. I don't want to assume everyone is familiar with Hodge-shaped weights, so I want to first spend some time just recalling how Hodge-shaped weights are defined and yeah. Any other questions? Okay. Okay, so yeah, as I say, so I want to first remind you how to define Hodge-shaped weights. But actually, I also not just Hodge-shaped weights, but the so-called Hodge-state sim weights, because the weights can be very general. So that's really the theory developed by Sen, a series of papers. So let me try to summarize the results proved by Sen in a couple of results. So what Sen proved is the following. So if you have a K, let me assume it's a p-adic field inside of QP bar, which really just mean that it's a discrete evaluation field. Okay, and if you have a continuous representation, continuous action of GK, so this is absolute Galois group of K, acting on a finite dimensional vector space over QP. Okay, and then Sen constructed this notation might not be very good, but let me use it. An operator theta V inside the endomorphism V tensor CP. is CP linear. So here CP is, as usual, denote the completion of the algebraic closure of QP. Oh. Okay, so some constructed element zeta V called the Sen operator. And satisfying following properties. So first is that, sorry, this is over QP, and so GK also acts on CP, so there's a semi-linear action of GK, and actually zeta V commutes with the semi-linear action of GK. The first statement. So it's CP linear and commutes with the GK action. And also it behaves, well, I should say also functorial in V. It's right here, functorial. And also it is compatible with taking direct sum and tensor products and taking du. So in short, it really behaves like a derivative. A derivation. So which really means that if you take the direct sum, it's just the sum of the Sen operator, and if you take the tensor product, it's really just it satisfies the usual Leibniz rule. And you can imagine taking du is just the negative of it. It's just that it behaves like a derivation. Actually, it's clear from its construction. I will just say, I will tell you what construction is at the end. But I think the first probably is better just to have some idea what kind of basic properties does it have. Next is that what do I call? Well, after at this moment it can still be 0, but just for the usual tape twist, actually it's just 1. Okay, and there are many more, but let me just say one more, which is that it helps you to compute Galois cohomology. So if we want to, like this goes back to Tate, like we want to understand this Galois cohomology. And actually, it turns out that it can compute it by some very explicit complex. So just naturally isomorphic to take this complex, two-term complex given by this Sen operator. Actually, it's just base change of this because this is still a K vector space. So if you base change to CP, you just get this. Okay, so in particular, this only has 2 terms, so it only has H0 and H1. There's no H2. And you can see H0 is very explicit. Well, H1 is also, but okay. And the hot-shaped waves, so usually what we call like depending on the normalization, but for me, I would put in the sign here. So the eigenvalues of the Sen operator are called hot-shaped. So some people call generalized hot-shaped weights, or I would call hot-shaped Sen weights of V. Yeah, and so this can be in general just a p-adic number. Now I want to make one remark here that yeah.
In Formula 4, well, there is a natural Galois action on the left-hand part.
Yes.
What is the corresponding action on the right-hand part?
It's not easy to see, but but there is.
And is it actually on the complex or on the cohomology?
No, I think it. Sorry, I think it should just be the semi-linear action of GK on each term. You're asking, so there's a GK action just on CP here. Sorry,
Yes, yes.
Yeah, I think it's just the semi-linear action.
Just semi-linear action.
Yeah. So yeah, maybe the best way to answer your question is give you another way to formulate this. And so the best way sort of to think about this V tensor CP is you should really think that this defines a co-eta vector bundle on SPA of K. Okay, so why? So you should imagine QP bar is the pro-eta cover of SPA K. And the vector bundle on that is really just a finite dimensional CP vector space equipped with a semi-linear of GK. So this, so what's actually really proof is that, I mean, in this case, there's really not much big difference between a star with a Galois representation and tensor with CP. But later on it will be different. So what's really proof is that in some sense, for any vector bundle, I can define such a Sen operator, and this commutes with this is a CP linear, which just means it's linear, and then commutes with the GK action, which just means it's really endomorphism in the pro-eta side. So it's really this theta V is really defines a I don't know what to let me call it W. So you should really regard that as an something in the endomorphism of W as a vector bundle, pro-eta vector bundle. And this last, you should really think that this left-hand side is computing some pro-eta homology. And this tensor CP is exactly like I pull back to the pro-eta side. Should probably just write down what I just said. So, okay. And the last four is really just saying that if you push forward, you compute the pro-eta homology, and then you pull back to you pull back, and then you just get this HI of this complex. I mean, let me call theta W. Maybe just another way to reformulate the. And I want to say, so this is something Sen did in 60s, 70s, but later, actually, 80s, later 80s, 90s, Sen also actually generalized this not just to infinite dimensional setting. But it's not true for arbitrary infinite dimensional Galois representation. You have to be careful. What do you mean by infinite dimensional? And I think Sen in his paper, he found the correct one, even though for a very long time I didn't realize it. So his setup is as follows. So if you have a p-adic Banach algebra, not necessarily commutative. And say you have a homomorphism from GK to A cross. Okay, now the key assumption here is that you want it to be continuous. So A is a p-adic Banach algebra. So when you take its units, it has a natural p-adic topology on it. So equivalently, if you quotient by 1 plus p to the n of the unit ball, so now this becomes a discrete thing. And if you want this continuous, that just means that this map has finite image for any n. And once you have that, then also can define Sen operator. Yeah. This Sen operator. Now it's a complete tensor product of CP. And yeah, I'm not going to repeat, but basically all these conditions will hold. Okay. So
So is A going to be like endomorphisms of the original?
yeah. To recover that, you just take the matrix algebra.
Okay.
Yeah. So if you take A is the endomorphism algebra, endomorphism ring of finite dimensional vector space, so you just recover that.
So is there also a lot of more general string theory when you have a semi-linear action to start with in this set?
Yes.
Okay.
Yes.
Sorry.
Thank you. No. That's a very good question. So let me first recover this theta v. And remark is that so in general, let me use a different notation. So V over CP. So CP Banach algebra. I want to say, and okay, maybe I'm not going to do this generality. Sorry, still just A, but instead of just a homomorphism, but instead you look at a cocycle. So Z1 with A taking value in, sorry, not A, GK. If you start with a continuous cocycle here, basically semi-linear representations element here, then you can just define. No, forget about that. Yeah, I would just consider all of this.
Also, it's a big question, but still, you can get around these basic completions of the bar with some kind of topologies and defined by OCP bar. And do we have some sort of deep around understanding using this story?
Sorry, which?
Well, there is a theorem of LMS. Describes deep around this.
Yes.
And I just wonder that if here you put instead of CP, you will put this final completion in the bar. Would there be similar theory?
Yes. The beta arm one, yes. At least for beta arm one, yes, there's a similar story. But the proof is really just because you can filter it by CP with state twisted, then you just reduce to this. So it will follow formally from this once you do all this. Yes. But I want to give you one more example. Because this example is still not quite really infinite dimensional. I learned this from a paper arbitrary commits. So the setup is the follow. So you take a Galois extension of K, it's like QP bar, and say the Galois group is G, which is a p-adic Lie group. Finite dimensional p-adic Lie group. So just some closed subgroup of GLM QP. Then what you can consider is the GK action value. G is really a quotient of GK. Then it acts on the space of all the analytic functions on G. So I'm being a bit vague here what I really mean by analytic, but let's say this G has you fix some kind of analytic structure, and then you can consider it's the analytic functions on it, and this section.
Local analytic.
At the end I want to do locally analytic. Then let me put here. So locally analytic is really doesn't quite satisfy that because it's not a Banach space, but it's a direct union of a Banach space. If you allow me to do that, if you admit that actually you can generalize also to this kind of direct limit of Banach algebra stuff, then yeah, let me just click here. Yeah. So if you consider all the locally analytic function, this means that around each point is given by a convergent power series. It turns out that well, this is the usual left regular representation. So just take the translation on the left action. And you get GK to the endomorphism of let me just call it CLA. And actually this is continuous. Okay, so this crucially uses actually is local analytic, but not continuous. Okay, so let me just make this remark here. This is false. I mean, this continuity. If CLA is replaced by all the continuous functions, space of continuous functions.
You said GK acts with G is active, right?
Sorry. This should. Yeah. GK acts through G.
And everything would work with G.
Yeah.
And just it's also the last fact is a general statement about stuff.
You mean this?
Yeah.
This one or this one? This continuity or this is non-continuity?
Sorry, the continuity.
Yeah. Yes. Yeah. I think it's more. Yeah. It works for very general. So actually, that's why some sense that you introduce this kind of locally analytic function. You have to introduce this here. But anyway, if this is continuous, then you have the then you can apply sense result, and what do you get? And you just get let me denote by theta CLA, which is the endomorphism of the CLA tensor with CP. You get the same operator here. But now you erase that, but I told you it's functorial. So here on this space, I also have a right the right translation action of G, and which commutes with the left regular action. So this commutes with right the action, right regular. No, G. And also it really behaves like a derivation. And so we all know that that's exactly the definition of the algebra. So you just look at the space of functions, and you have an invariant, right G invariant derivative. Then so that just means it's really maybe let me denote by let me just call it theta L. Really, it's an element in VG and service. So this is also originally already proved by Sen. But or maybe so you should think that this is the Sen operator for this extension, and if we assume this is non-zero, okay, and the Sen actually proved that there are several equivalent ways to think about this. One equivalent way, well, using the modern language, is that L hat is perfectoid. But if you want the most elementary way, also proved by Sen, is that actually L is not a p-adic. The valuation on L is not discrete. Well, equivalently, the ramification index is infinite. Yeah, so they are already equivalent. Okay. If we assume we are in that case, then I erase that. So now if we compute we can try to compute. Now let me take V to be CLA. And then try to compute the Galois cohomology of its tensor product with C. And try to make use of this property. Okay, on the left-hand side, so I have the Galois cohomology of CLA G QP tensor with CP. But when I tensor with CP, basically I'm looking at the CP value function. I can just put CP value here. And if I base change to CP, it's isomorphic to this complex, cohomology of this complex. But if theta is not zero, you can easily show actually this is surjective. Okay, basically it's like it's some kind of usually you're just computing the wrong cohomology of a fine line. This is really not a fine line, but over convergent neighborhood of a point in this. So this you can really compute the just in degree 0. Okay. No. So this just tells you it only has H1, sorry, H0. But let's look at what is really computes. So first, the GK action factors for CP. I mean, the action on G factors through G. So if you just take the Galois group of L, first take that invariant, you just get the CP GL invariant of CP. So this is really just CLA G valued in CP GL. So with CP. Okay. So here, I mean, already there's no higher HI. Actually, I'm only caring about H0. So this and this by a result of Tate. This is just the completion accident Tate. This is just L hat. Right. So if I'm just doing L equal to 0 here, so the left hand side is really just a complete tensor product of CP of this CLA G taking value in L hat, and now I'm taking G invariance. But when I'm taking G invariance, it's exactly I'm taking the G locally analytic vectors in L hat. Why? So there's an obvious map from here to here because this is just the orbit map. Like if I start with an element here, I get a function on G just by look at the orbit. And because it's a locally analytic vector, so the orbit map just give me a locally analytic function. And actually, you can prove this really is just an identity. So what you see on the left-hand side is you're just essentially computing the locally analytic vector of L hat, and the right-hand and the tensor is CP. Right-hand side, what you get is just a CLA, and you look at all the functions annihilated by this Sen operator. So you get this result. The conclusion is that L hat GLA, I didn't quite explain what tensor product is. It's really tensor product for LB space. It's just naturally equal to all the local analytic functions on G, and which is annihilated by the Sen operator. So one corollary is that you see these locally analytic vectors, you can ignore the CP naturally satisfies some first order differential equation. And I don't think I have time today, but yeah, next time you will see what it will replace in the geometry setup. And also this first and the second corollary is you see that there's no higher cohomology when you compute this cohomology, and some people call that this L hat. When you take this locally analytic vector, if you take it in the derived sense, there's no higher HI still. And you see all this computation actually is just completely come from our understanding of this Sen operator. So once we understand this, all these just follow very formally. Okay.
Sorry, in the analogy to the complex case, data we thought it's just Casimir or as
the Cauchy-Riemann. Yeah, it's a first order. Casimir is like second order. Because yeah, so I want to other questions. I want to quickly just tell you how Sen is constructed, and probably say a few words. Anyway, I think I need to repeat it next time, but at least I want to at least tell you now if we want to generalize all this. I think once you understand this pretty well, it should be very clear. I think everyone can do it. So how to generalize to the geometry picture. But let me just quickly tell you the construction. And I should say this construction really goes back to Tate. Of course, the Sen is the student of Tate, so that's not surprising. But I don't know if you read Tate's paper on p-divisible group, you should have already seen this. So essentially, you're doing so you have a QP bar and K, and there is some intermediate step which denoted by K infinity, which is K adjoint all T roots of unity. And let me denote the Galois group of this by HK, so G K infinity, and this denoted by gamma K, which by cyclotomic character is really an open subgroup of CP cross. Okay, so the first step, so is if we start, I would just say do the finite dimensional thing, but actually it holds infinite dimensionally if you do the continuous, if it's continuous. But V tensor CP, the first thing is that you descend from QP bar to K infinity. Okay, so but that's basically nowadays usually it's called the almost eta descent. Is equal to, you first take HK invariance. So it's a K infinity vector space, but actually it's p-adic complete. So it's actually vector space over K infinity hat in tensor CP. Actually, this was already known by Tate, simply because nowadays you can either say the extension from QP bar to K infinity is almost eta, but yeah. So this step doesn't use much, but now now it's really from K infinity to K. So now we have because this is the HK invariant, so there's a gamma K action. And now it's really about how to understand this gamma K action. And so what's then actually proof is that if you take the gamma K locally analytic vectors. Okay. So again, well, this case you can't really apply Schneider type of bombs results. It's not admissible. So a priori it's not clear there is locally analytic vector. But actually what's then proof is that there exists actually the form of basis over CP, which just means that if you tensor with CP, you just get back to your V tensor with CP. And what is this tensor product over? Well, because gamma K, so I'm looking at locally analytic vectors, but K infinity, the action of gamma K, so each element here is fixed by an open subgroup of gamma K. So it's a locally analytic vector. So it's a vector space over K infinity. Okay, so the difference is this is really the completed one. This is not. But so you really can decomplete this by taking gamma K locally analytic vector. So this step usually called decompletion. And it's usually the most, I would say technically the most complicated step. But once you establish this, then the existence of Sen operator is clear. Because now once you take gamma K locally analytic vector, then you have the action of the Lie ultra of gamma K. But gamma K, by using cyclotomic character, is just ZP cross. So its Lie ultra is just QP. Just by taking logarithm. So you have a canonical element 1 here, canonical generator here, and that gives you the and moreover, I said so K infinity, each element is fixed by an open subgroup of gamma K. So the Lie ultra really acts as 0 here. So it's really K infinity linear. This is the K infinity linear. So in particular, you can extend this action CP linear to the tensor product, and that gives me the Sen operator. Okay, so that's the complete the construction. So for the infinite dimensional thing, you can imagine. So the continuity assumption basically tells you you can do this step of decompletion, and this continuous property in some sense it just tells you actually there are enough. You can deduce that there are enough locally analytic vectors. So I'm not going to really go into detail, but yeah, so it can be done. Yeah, Yeah, so that's what I want to say about the construction of the question. So I wanted to say that so here originally Sen didn't really, I think he was following Tate. So he was not really taking the gamma k locally analytic vectors, but he was taking gamma k finite vectors. And it was really pointed out by Bourget and Comes that taking locally analytic vectors is the correct thing to do. So this is the I'm not sure that's why people, in this century start to understand this much better. And also, I found that this quite interesting. Like this work of Sen really goes back to last century, maybe 60s or 70s. And I think if you think about it, like the key thing is really to take the locally analytic vectors. And in some sense, for people doing Rex theory, they already knew this, like taking locally analytic vectors. If you think about the work of Harshchandra, like it's clear that's the thing you need to do. But yeah, I think for p-adic people didn't quite realize that for some time. So anyway, so quickly I want to just say how to generalize this to the geometric case. So I want to just draw a table here. So here on the one side you have a spot k, or just k, and here I'm going to replace it by origin analytic variety over CP. And for simplicity, I will just well, not for simplicity, I will just always assume it's smooth of dimension d. Okay, and you just want to repeat everything. So for example, well, here I have a Galois representation. Well, here I can just look at the pro-état local system. And here I have a V tensor with CP with the semi-linear action of GK. Here I just tensor with the structure sheaf of the completed structure sheaf on the pro-état side. Oh, that's next. Structure sheaf on the pro-état side. And again, here is the vector bundle, pro-état vector bundle on spot K. And this is the pro-état vector bundle on X. And I should say there are many more pro-état vector bundle coming from this way. It's like in the complex case, so you have a line bundle of the non-zero degree and won't come from this way. Okay, and so then Sam just let me give a name. Sam has a Sam operator here. We'll try to finish in 5. So here on the you have a Sam operator, and on this side, some people call it a geometric Sam operator. I will just follow them. Okay, but here you remember. Plus, it's just the endomorphism of this vector bundle, right? But here, you don't get the endomorphism. But what you get is Let me give a thing. So from W to itself, but now you need to twist by the differential operator, the cotangent space. And there's a tape twist here. Which is a Higgs field. Well, which really just means that this is OXF linear. And if its value of itself is just a 0. So locally, the dimension D, you're just getting D operators. And this just is, in some sense, that they all commute with each other. And why you get the D instead of just Y in this case? Well, that's simply because also, where does this come from? I can't quite give you an answer, but at least locally, so in the local field case, you have this K infinity, which is by joining all the piece roots of unity. And this gamma K is really one-dimensional. And if you remember, the construction really comes from the derivative action. So by one-dimensional, the algebra only gives you one operator. And here, the analog here is that you look at the torus. And then you replace and then you look at the cover just by extracting roots of these coordinates. Let me call it T infinity. I'm not going to write down the integral part. But this cover, because I have D coordinates, so this really just it's a ZP1 to the D cover. Okay, and you see now this is the D dimensional, and so locally, if you think this is the local picture, well, in reality, locally we will just choose some finite tau and open immersion into this kind of thing. But locally, you just get you get the D operator, so that's why you don't get just one. And unlike the local case here is just this is really canonical, right? This tower here, it depends on the choose of coordinates. So if you want to glue it at the end, it turns out that the correct thing is you put the cotangent G here. Okay, so I think I will just stop here. So, but the point is that now you can do this for region analytic variety. So next time I want to explain how to actually calculate this in some case. Okay, I didn't tell you the definition, but I hope you can imagine. Basically, you just try to do the same construction. Also, as usual, you are really not computing things based on the original definition. So next thing, actually, what we will do is we will try to relate this to p-adic Simpson and use p-adic Simpson to compute this. But I'll be able to explain to you that next Monday. Thanks.
But that's thing that doesn't depend on the future story forward.
Locally, if you write in this form, no. Yeah. So yeah, a priori this is, but I think secretly in this case you have a canonical choice of the basis here, just given by dti over ti, and once you use that, you can actually verify it's independent of this coordinate. Yeah.
So does this also exist when you start off with S over K? You just get like E plus 1 range?
Yes, but they won't commute. Like the arithmetic one doesn't commute with the geometric one. Yes.
What is the commutation zone?
I think that just the commutator is really like this then, like usually imagine it's like I don't know, something like for me is doesn't make sense. I think you understand pretty well what's the commutator. Basically, the commutator here is here. Sorry, yeah. Yeah, just the
-1.
Hmm?
-1.
Yeah, there's minus. Yeah. Yeah, I think the commutator here just.
Any other questions for the speaker? If there are no questions, let's thank the speaker.